Hey, look up. Okay, no one talk. Okay, so I jumped right to the first problem in the packet that's labeled as an extra example. So I think if you turn the page, you'll see that. I think it's on the second page. So it says extra example 2E. The ones that are labeled as extra examples, FRQs are a little harder to type up the answers for. So there's no answer in the back for the ones that are labeled as extra examples. We'll try to get all of those completed during class so that we can just kind of check them together. This problem is not new. It's straight from the yellow. I mean, it's the same concept we talked about on the yellow packet. Again, they give a table. The table simply shows the water temperature at different days. They ask us to use the data from the table. So we're supposed to use the table to approximate W prime of 7. W prime of 7 would represent how fast the water temperature is changing precisely on day 7. So just like we did new seats, Matt, so you can just choose whichever seat is open and sit there, and I'll call that your permanent spot. So anyway, W prime of 7 represents the rate at which the water temperature is changing on day 7. So just like last time, what I do is I notice that I really have no way to find that. That's why they're asking me to approximate it. So what I notice is on day 9, the water temperature is 24. On day 6, the water temperature is 28. So during that 3-day period, the average rate of water temperature change is going to be -4 degrees Celsius over a period of 3 days. That's an average rate of change, or a secant slope, and I'm using that to approximate an instantaneous rate of change, or a tangent slope. And I wouldn't go any further. That will get me full credit on the test. So, questions about anything? Please.
Last class you assumed that you could just stop with the 24 minus 28 over 9 minus 6.
Yes. So what happened? No, really good question, Eric. It's kind of just my habit to keep going because I feel like this sticks in your head a little bit better as far as what it really means. But I want to back up a step because I agree completely with what you just said. So I went this far because mentally I can process the meaning of that easier than I can this. So when I see this value, I'm like, okay, that makes sense. On average, and if we grabbed a calculator, that's going to come out to be 1.33. So that's like an easier way for me to understand average rate of change. But I want to follow your recommendation on the actual test. I want to just write, W prime of 7. I have to show my computations because it is explicitly stated in the instructions that I must. I have to show units, so I definitely want to do that. But Eric is correct. On the actual AP test, that would be your best thing to do. Is that what you meant?
Yeah.
Perfect. There you go. The key things to memorize. It's very common for them to ask you to approximate a tangent slope by calculating the nearest secant slope. That's what we just did. That's equivalent to them saying calculate an instantaneous rate of change, and we do that by calculating an average rate of change. So we approximate an instantaneous rate of change by calculating an average rate of change. Okay, next thing. So go to the next extra example, which is 2F. This one also is not new. It says approximate the average temperature in degrees Celsius of the water over the time interval using W of t and a midpoint Riemann sum. Key things to notice. They're asking us to find average temperature. We want to pay attention to units because they often pay for units. The time interval is crucial. And what I'm supposed to use is crucial. Midpoint sum, the subintervals of 6 days. So those are all the key items I need to pay attention to. I believe last time I tried to emphasize heavily that going forward as we work with integrals, we increasingly need to pay attention to the thought of why are we doing an integral. And then the second question is always going to be, actually not always, sometimes it's actually somewhat common to have AP questions where they stop here. They don't ask you to actually compute the integral, they just ask you to write the integral, and they give you points for that. But once we know why we're integrating, we often do have to think about, okay, how are we supposed to perform the integration? So how to integrate. Bad grammar here. So in this problem statement, they're covering both of those items. They're talking about why we should integrate, and they're also talking about how to integrate. The why is we are going to use an integral to calculate the average temperature of the water. So the integral I create looks like this. I'm going to integrate whatever I am averaging. So because I'm averaging W, water temperature, that's what I integrate. Make sure, since this variable is t, this has to be dt. I want to find that average over a period from day 3 to day 15. And because this is an average, I have to divide. So I've got to have this out front. That's the why right here. That's not the how, that's just the why we are integrating. Question? Please.
As I've been doing it on my own, I've had a hard time knowing when to use an integral and when to just find the slope. So how, in this problem, what shows you that you're finding this Riemann sum? Like why did you go to that?
Let me see if I can help a little bit. 2 points for David. This one I would say straight memorization, to be honest. Like I simply have a flashcard that says something like this. The front side of the flashcard says find the average. Of just whatever. And then the back side of the card says I'm going to integrate whatever I'm averaging over some time period. So I would say that one's straight memorization. Like I'm not really using any logic. I've just got a card that's telling me, reminding me that when they ask me to find the average of something, that's what I do. Does that make sense? So not a great explanation, but that's really how I do that one. This one here, by comparison, this one was more logical. Like I know that this is asking me for a rate. So finding a rate is somehow related to finding a derivative. But I realize immediately that I have no way of doing that because I don't have any formula. So the best I can do is say, well, I know derivative, I know rate means slope, and so that's why I went and found the slope here. I hope that's helping though.
Yeah.
Okay, two more actually. So back here, again, one thing David said that I want you to be careful about is at this point in the problem, you should not be thinking Riemann sum at all. This is simply the why we are integrating, and you'll never see me put a Riemann sum here because that would be incorrect. Riemann sum is not why we integrate. Riemann sum is how we integrate. It's a technique for computing an integral. So don't think of Riemann sum yet. All you should be thinking is, hey, I've got to find the average of something. In order to find the average, I've got to integrate whatever I'm averaging. So start with this. Now we move on to how are we supposed to compute that integral. So really, I made one small error here. All of the orange items are related to, I just circled this incorrectly. All of the orange items are related to the y. Like, why are we integrating? We're integrating to find the average temperature in degrees Celsius over this time period, and we're going to integrate whatever it is we're trying to find the average of. So all of the orange relate to why we are integrating. The purple, that's how we integrate. So now I put this integral is equivalent to, don't forget the constant here. You can write that as 1 over 12, that's fine. Okay, everything I'm going to put inside the parenthesis now in green is the computation of the integral. The 1 over 12 was not part of the integral. The integral is just this portion here. So inside that green parenthesis, I'm going to approximate the integral. To integrate means I am supposed to multiply these two items repeatedly. So I look at my table of WT values. I'm supposed to start here at day 3, stop at day 15, make subintervals that are 6 days long, like that. So midpoint means go to the middle of each subinterval. Go to the middle of each subinterval. So I take the middle value of W, 28. That gets multiplied by the duration of time for the subinterval. Duration of time for the subinterval, which would be 6 days. I add to that this value of W, which is 22. And the duration of time for the subinterval is again 6 days. Close parenthesis, don't forget the units, I'm done. Questions about anything?
How do you know which units?
The quickest way to determine the units is just to think about what they're asking you to find. So I'll get you to say it and it will stick better. So what are they asking you to find? Right. Yeah, in fact, they actually state it. So this is just a computation. So average just means, well, I've got all these different temperatures. If I were to average them, what temperature do I come up with? And so I know this has to be the same as the units of temperature. Does that make sense? 2 points. Anybody else? Cool. Next thing. Moving on. So that was both review for the yellow packet. Go to the next extra example, so it's in a couple of pages over. Extra example 3E. We may have mentioned this concept earlier this year, but I honestly don't remember. It's been so long. We're back to talking about a moving object. So an object moves along the x-axis. Please remember that when they talk about an object moving along the x-axis, they're referring to something like this, where here's a horizontal line, and there's some particle that's moving along this line. You should not be thinking of this as a graph. It won't help if you think of that as a graph. It's not. It's just a picture. It's like you ask a third grader to draw a picture of something moving along a line. That's what they'll draw. They don't know anything about graphs. Okay? The particle simply moves to the right, or the particle moves, to the left. But it's not a graph at all. So that's the particle moving along the x-axis. The initial position at time 0 is 2. So this statement, x of 0 equals 2, is telling me that right here is where the particle starts its movement, and this is time equals 0, and this is labeled as location 2 along the line. This is known as the origin. Origin doesn't mean original. Origin simply means the center. Okay, I wish they'd give it a different name, but they didn't. So, question. Cool. Then they give us a formula for the velocity. One of the most important things about this problem is that it is calculator allowed, as are all problems in Unit 4. It's going to make my work a lot easier. I don't have to do anything by hand. I can just keep using my calculator. They want to know at time equal 4, is the object speeding up or slowing down? Okay. Most people think that the way to answer this question is to go find the object's speed, say at, time 3.9. And then compare that to the object's speed at time 4. And they feel like by comparing those two speeds, they can determine whether the object is speeding up or slowing down. The trouble is, the grader can easily say, I can't give you any points for that because you didn't consider what's happening at, say, time equal 3.99. Like you left a gap of time. And there's literally no way to eliminate that time gap. So don't ever try to answer this question by looking at two different times. Don't ever try to answer this question by looking at two different times. We're going to focus completely on one time. Time equal 4, and that's it. And that's what you have to do. There's a lot of questions on the AP test every year that talk about whether something's increasing or decreasing. You cannot answer those questions by looking at different times. You have to answer the question by looking at one time. Question. So here's where we start. We're going to go find the velocity of the particle at time equal 4. It's not very difficult because we're allowed to use our calculator. So, 2002 3E. So I've got it all set up here already. So there's the formula that they gave us in the problem. All I have to do is go to the main screen. I've showed you this before. I choose y1 because y1 is the velocity. I plug into y1 a time of 4. And I'm going to write that down, negative 0.866. Just wave at me if you need me to go through the calculator steps again. I don't mind at all. So. Okay, so we're good? Okay, this problem doesn't have any units associated with it. I'm going to add some units because it makes the explanation a little bit easier. It points for the whole room. If I state that the velocity of this particle is negative we'll just say negative 0.8, just rounding so talking is easier. If I state that the velocity of this particle is negative 0.8 meters per second, what does that mean? You have to know the meaning. If you try to succeed in this class by just doing steps, you will not succeed. It's got to make sense to you. Hands up, one. What does it mean? It's not a complicated meaning, just what's the simple meaning of the velocity at time 4 is negative 0.8 meters per second. What does that mean? About half of you. We'll wait for a few more. There we go. Let's go, Edward.
That the object is slowing down.
2 points, but no. It's okay. Common mistake. The negative doesn't mean has anything to do with slowing, so it's good to bring it up. 2 points. Hands up. What does it mean to say negative 0.8 meters per second? Let's go, Daniel.
Moving to the left of the velocity of 0.866.
So this particle, the negative means the particle is moving left. Hands up if you knew that. Hands. 2 points. 3 for Daniel. So the negative simply means the particle is moving left. It doesn't have anything to do with slowing or speeding up. It's just moving left. 0.8 means if you take out a ruler, you could literally measure the movement. This ruler is a meter stick. 0.8 is right there. So that means the object moves this much every second to the left. Question? Please.
So stuff like that doesn't tell us if it's slowing or speeding.
Correct. Seems like a simple comment, but I'm going to pay a ticket for it. Look up. If all you know is the velocity at a given instant, you do not know whether the particle is speeding up or slowing down ever. All you know is that at that instant, the particle's wanting to move that way that much in 1 second. Now, with calculus, everything's changing, so that doesn't really happen. That's how you should be thinking is, okay, the particle is moving, and at that moment, it wants to be moving that much over the next second of time. Okay, but we don't know whether it's speeding up or slowing down. Please, Herb.
Would that be the point where you try to take the acceleration, find the acceleration of it?
Nicely done. Because remember, the grader's not going to give you any credit if you go looking for like what's happening at time 4.1, because there'll always be a time gap. You can't get rid of it. So what we do instead is what Eric said. We're going to go find the acceleration at time 4. And because we can use our calculator, it's really easy. We also did this early in the year, but it's been a while. You type math 8. And just plug everything in. And write it down. Just wave at me if you need me to show the keystrokes again. Awesome. Okay, what this is telling us is, you notice, velocity indicates how much the position wants to change. Velocity indicates how much the position wants to change. You have a particle, it's located somewhere. That velocity of negative 0.8 is saying, hey, I want to move negative 0.8 meters to the left during the next 1 second of time. The acceleration tells you how the velocity wants to change. Everything's changing simultaneously and instantaneously, so it doesn't really unfold in a simple manner, but this is the best way to think about it. My velocity right now at time 4 is negative 0.866 meters per second. The acceleration at time 4 is indicating how much this wants to change. Meaning that if I could hold everything kind of steady and just let this happen, I could actually predict the velocity at time 5. I'll pay everyone to do that. Talk to each other, raise your hand, and tell me what would be, like if everything were allowed to kind of remain stable, meaning this actually occurred, the velocity would change by this amount, this many meters per second, over the next 1 second of time. Talk to each other and raise your hand and tell me what would be the new velocity at time equal 5. Looking for hands. Somebody will get it. You can use your calculator if you want. David's in, Matt's in, Zarin, Eric, Daniel, Edward, Carl, Allison. Keep wanting to call Jessica because I missed his name on a list yesterday. Some old reports. Hey, it's Allison's sister. Hands up. What's the velocity going to be if everything stays as written on the board? What will the velocity be, Zarin, at time 5?
Would it be 1.39?
Positive or negative?
Negative, sorry. Yeah, negative.
Is that correct to 3 decimals by chance?
1.390.
Thank you. Okay, look up. Hey, I say it all the time, but you have to make sense of the idea. If you memorize the step, you'll forget it. Okay? You have to make sense of the idea. This is the velocity at time 4. Acceleration tells us by what amount is the velocity going to change in the next second. So all Zarin did was say, well, I currently have 0.8 meters per second, negative. Acceleration is telling you that that velocity is going to become even more negative in the next second. How much more negative? This much more negative. So he just adds those together. This is his new velocity at time 5. That's not really what happens because everything's changing simultaneously. Like the acceleration does not stay at this amount for the entire second. But it's good enough to give us an idea of what's happening. Okay, show me your hands if you figured this out in 47. 2.3 for Zarin. Okay. You want me to talk more about it? Questions, anything? Please.
I just want to make sure the object is slowing down.
So in this case, the object is actually speeding up. Because, no, stay with me, Paul, you'll see it. So are you okay that the velocity at time 4 is this? The velocity wants to become this. It doesn't really become that, but it wants to. Are you okay with that? Okay. So the negative indicates what?
It's moving left.
Moving left. It's wanting to move left 0.8 meters every second. That would not be what I wanted to do. Wants to move left 0.8 meters every second. But if we allow the acceleration to do its thing, now the particle wants to move negative 1.4 meters every second. So it's really speeding up as it goes to the left. Does that make sense?
Yeah.
3 point. You else want to talk more about it? Please.
Do you have to like write it speeding up or just show your work?
Awesome. So what I have to write, points for Emmy, I have to show this. I have to tell the grader that I understand what the velocity is at time 4. I have to show the grader that I understand what the velocity is at time, sorry, the acceleration is at time 4. This thing in orange I'm not going to show the grader because it's not really true. That was just me trying to help you all understand the idea. Then I'm simply going to write on my paper this, because they say I must justify my answer. The justification is basically these two statements combined with this sentence. And that will give me usually 2 points on a question like this. 2 points for every.
Do you need a unit as well?
Now remember, good question, 2 for David. If the problem had units specified, you would definitely want to list them. Because this problem doesn't have any units specified, it doesn't matter. So that was just me trying to make it easier to talk about.
So this is minor syntax. So the question talks about an object and you wrote a particle. So is that,
Oh,
is
gotcha.
that worth a mention?
Worth a mention, I don't think they'll have a problem with it.
Okay.
Good comment. Yeah, I just have done too many AP problems where they talk about particles and I just didn't even think about it. Yeah, I think you're okay on something like that. I've never seen them be that picky, so. Question 2 for David. If you stop using the eraser, I could concentrate. 2 for Edward, sorry for the wrong name.
Thank you.
Other questions, anything? Please, Alex.
I didn't use why the particle is actually speeding up.
No worries. Try this, see if it helps. We're going to pay points to the whole room. Okay. This is a really simple example. You're not likely to encounter anything this simple on the AP test, but if you can understand the simple example, it's easy to understand the more complicated. So I'm saying the acceleration is always 3. Always. Acceleration tells you how velocity changes. So we'll say this is 3 meters per second every second. Raise your hand if you know what the velocity will be at time 1. In this simple example, this is absolutely true. Like the previous example, we kind of had to pretend that the acceleration wasn't changing. Here we're stating the acceleration is not changing. Acceleration tells you how the velocity will change. The velocity is currently 8 meters per second. This might help. You have to put your hands down for a second. You have to think of velocity 2 different ways. When I'm thinking of velocity as it relates to position, I think of the meters and the seconds separately. I think to myself, 8 meters per second means that every time 1 second of time elapses, I will move 8 meters to the right. So I think of meters and seconds separately. When I'm thinking of how velocity relates to acceleration, I don't. I think of meters per second as like one thing. So I've got a velocity of 8 meters per second. That velocity is going to change in the next second based on what the acceleration is. The acceleration is saying your velocity is going to be different by 3 meters per second in the next 1 second. That's how the velocity is going to change. So hands up again. What's the velocity at time 1? There we go. Well, Lexi.
Would it be 11?
Perfect. And then keep going here for a second, Lexi. What's the velocity at time 2?
14. 7.
How many knew it? 2 points, 3 for Lexi. So look at this object and tell me, just say it out loud, is the object moving right or left? Hands up. Sorry, just say it, right or left? Right. Good. Is the object speeding up or slowing down? Say it. Speeding up. Because the velocity is becoming increasingly positive. The particle is moving right, and the velocity is getting more and more positive. The particle is speeding up. Question? Now change the situation. Make this negative. Let's go here. Meters per second every second. Hands up, what's the velocity at time 1? Let's go Cambria. And then time 2, Cambria. And time 3. Hands up, Newark. Towards street for Cambria. Please say it out loud. Is the particle moving left or right? Say it.
Right.
Right. A little weak there. You know. Say it out loud. Just say it out loud, please. Slowing or speeding up? Say it. Slowing. It's moving to the right, but as it moves to the right, it is slowing because the acceleration is what causes the velocity to change. But the acceleration is a measure of how the velocity changes. There, please.
So does that mean if we waited till time like 5 or so, when the velocity goes to 0 and then it transitions to like moving left, would that mean that it's starting to speed up then?
Absolutely.
Just to the left?
Mm-hmm. Helps if I write the right numbers here. I'm putting them all over the map. Hold on.
We wouldn't have it.
Yeah.
This is the new
Yeah.
unit of calculus.
There you go.
We would learn how to do
Back to the future.
Yes.
Marty McFly and all that, you know. Dr. Brown. Yes, if the acceleration is going to stay at -3, the particle will be, it's moving to the right. Here, the particle is still moving right, but as the particle is moving right, it is slowing. At time equal 5, the particle will stop. Then the particle will begin to move left, and as the particle moves left, the particle will be speeding up. There's a pattern here. It's really simple. If the signs of the acceleration and the velocity are the same, the particle will speed up, because you can think of it as they work together. Okay? The signs are opposite, the particle slows down. That's what you're seeing on the board. Question. Cool. Does that help? You can always say no. It doesn't hurt my feelings. You're okay? Good. Yeah, very serious about that. I've tried to say that all year. If I try to give an explanation, don't ever say yes, it helps. If it doesn't, just have the courage to say, you won't hurt my feelings at all. Just say, no, I still don't see it. It's never your fault that you're not seeing it. It's just my fault for not giving a good enough help. So, please.
I just want to point out, it's like I'm paying $100 for this class, so if I'm not going to get it, then I'm wasting like $100 of my own money. So
Yes. Yeah.
I'm going to take the time to understand this.
Hold on, payment for that.
I would also like to say that.
Yeah, I'll pay for that too. Okay. No, it's well said. And the way I look at it is, the tricky thing about learning complex material is I can never quite judge what the right thing to say will be so that it clicks for you. And that's why I need, like what Zaren said, I need you to just speak up and say, hey, no big deal, I don't get it. It doesn't matter, I don't. And then we just keep talking about it until you do. Because once it really becomes something you understand, you'll forget, but you'll remember way faster. Like when you need to. Is that going to do the make a good joke? Okay, good one. You're welcome. Okay, next thing. Extra example 3F. Oh yeah, please, Aaron.
With this one, can you just use like the same work from above to figure it out?
We will use part of the work above, but we do need some new work.
Okay.
And with every FRQ, the way the FRQs are laid out in the actual AP test, Jake's got a good binder here. You get a booklet. And when you open the booklet, it's going to look like that. And everything on both pages is considered one FRQ. So there will be information at the top, and then there'll be like part A, B, C, D, not usually E. I've never seen that. Last year was an exception. They wrote some brand new kind of weird tests for COVID. Anyway, whatever you do anywhere on the page is considered one big problem. So if I do some computation here and I need that number here, I can just use it. I don't have to restate anything. Is that what you meant?
Yeah.
Perfect. There we go. Cool. Hey, the way we solved this problem, though, is quite similar to the way we figured out whether the object was slowing down or speeding up. We, again, do not want to pay attention to any other time other than time equal 4. They won't give you credit if you try to solve the problem that way. So we're going to pay attention to what's happening at time equal 4. We already know that at time equal 4, the velocity is negative 0.866. You don't need to rewrite it. On the actual AP test, it would be like I just showed you. You'd be looking at one booklet so you could just see it. But since I had to flip the page on the monitor, it's a little hard to see. So we know the particle is moving left. We know that it wants to jump 0.8 meters every second. That's what that means. Okay? We don't know whether the particle is moving toward or away from the origin, however, because at this juncture, we don't know where the particle is. Here's my picture of the particle's movements. Here's the origin. If at time equal 4, the particle is located in this spot, and we know that at that moment the particle is moving left, that would tell us the particle is moving away from the origin. But it's possible that at time equal 4, the particle is actually right there, which means we'd have to tell the grader the particle is actually at the origin. It's not moving towards or away. At time equal 4, the particle is at the origin. I've never seen them ever do that, but they could. Or the particle could be here at time equal 4 and moving left, which means the particle would be moving towards the origin. Please.
Doesn't it just tell you that the initial position is 2?
Go on, Sarah.
That means like it would be in between the 0 and the 4, which means it would be moving towards the origin, right?
You're on the right track. Let's just keep talking. So let's just keep talking for a second. So we know that at time equals 0, I miswrote that. That's supposed to be time equal 4. We know that at time equals 0, the particle is at a location of 2. We're trying to figure out where the particle is at time 4. Does that make sense?
Yeah.
Yeah. So the time equal, what happened at where the particle is at time equals 0, that's important, but it's not sufficient for me to know. It's not sufficient for me to know where the particle is at time equal 4, which is what I have to figure out. Because again, we solve both of these problems by focusing on time equal 4. Does that make sense?
Yeah.
3 points. Okay. It doesn't do any good to go forward unless it makes sense to everyone that in order to figure out whether or not the particle at time equal 4, the object, is moving toward or away from the origin, I have to know 2 things. I have to know the velocity of the particle at time equal 4, and I have to know the position of the particle at time equal 4. The combination of those 2 items will tell me whether the particle is moving away or towards the origin. Question? Cool. So we need to go find the location of the particle at time equal 4. We're back to that idea of why are we doing an integral. We're going to do an integral because we want to find a position. And we're going to find the position by using the fundamental theorem of calculus. We studied the fundamental theorem on the buff packet. It's obviously been a little while. So here's a quick review. On the buff packet, you practiced writing a formula like this. The position at time 4, this is a version of the fundamental theorem, is equal to the position at time 0 plus the integral from 0 to 4 of the velocity. That is a version of the fundamental theorem that we studied on the buff packet. Questions about anything? Cool. So that's the why. We are creating this equation with the express purpose of finding the position of the particle at time equal 4. We learned in the buff packet that when we integrate velocity, we calculate displacement. The how to integrate is easy, because this is the calculator section of the AP test, and we have an equation for what we are integrating, so we can just use our calculator. Go back here, math 9, do the integral, 0 to 4. We want to integrate velocity, which is in y1. That tells me displacement, 1.432. I write that down. X of 0 is 2. So integrating the velocity tells me by what amount will the position's location be different from time 0 compared to time 4. The particle is actually moved to the right 1.432. The particle was already at location 2, so that means at time equal 4, the particle is at a location of 3.432. So now that I know the particle is at that location, I know the particle is over here somewhere. And at that moment, the velocity is negative, so the particle is moving towards the origin. Questions about anything? You want me to redo anything? Talk about it in more detail. Talk about it differently. Anything. Please. Yeah. So very similar to the last problem, I've got to have 2 points for Daniel. I've got to have listed on the paper the velocity, which I don't need to rewrite. Like Eric said, I've already written that in the previous portion, so I don't have to rewrite it. I must show the work for finding the position. Please remember, you want to make sure that every time you use an integral, you write down the integral. They often give points for it. So you need to have this on your paper. You don't have to have this step. I wrote that to hopefully improve your understanding. So I've got to have the blue boxes. Now I need a statement. The statement's pretty much like the last one. I say, since x of 4 is positive, so x of 4 being positive tells me I know that at time equal 4, the object is on the right side of the origin. And phi of 4 is negative, which tells me the particle is moving left. Therefore, the object is moving towards the origin. Please.
Can we abbreviate positive and negative as you did?
Very good question. 3 points, yes. I try to be really careful and only use abbreviations that are allowed on the AP test. You can kind of mimic what I'm doing. Those two are allowed, so well said. Once in a while, just to make classical a little faster, I'll write something like I don't think I've ever seen a question where I had to say anything about the fundamental theorem. So even though this abbreviation isn't technically allowed on the AP test. I'm not worried about it because it's never been needed. So, question? Please.
You have to say, since, you know, that this is positive and this is negative, the object is moving towards the origin? Or can you just say it's moving towards the origin? Like you show
question.
your work and then you just write it's moving towards
Awesome. Hold on. Everyone listen to this one. This is what Jonathan just said. It's very logical what you're thinking. It just turns out that the rules of the test are such that that would lose, you would only get one of 2 points. By stating the velocity, by stating the position, by stating that they're positive and negative, just showing that they're positive and negative, and then saying, oh, the object's moving towards the origin, they'll give you 1 point for the correct answer. They won't give you the point for justifying. So justifying is, in part, you simply learning what they expect. Yeah, they expect to see this. Good question. Please, Eric.
And then kind of going off of what Theorem is asking, for like positive and negative, can you like write like the symbol for positive and negative?
You can, yes. I don't like that because I feel like plus and minus can get mixed up with adding and subtracting. And so I tend to just feel more comfortable with the POS NEG abbreviation.
Okay.
That they would allow you to write this. Yeah, they'd be okay with that. What they usually do, well, I've never seen them actually use that kind of notation. I've seen them do what I did with the POS and NEG. They do this all the time. They'll go like this. Like that. That's acceptable too. There you go. Sweet. Keep going. There's a pattern here as well. If position and velocity are both positive, that would mean I just picture particles over here on the right. Positive velocity means I'm moving to the right, so I'm moving away from the origin. If position and velocity are both negative, I'm located here. Negative velocity means I'm moving that way, so I'm moving away. So if the signs of position and velocity match, the particle is always moving away from the origin. Cool. Number extra example 3G. It says calculate the average velocity of the object. That's straight review from the yellow packet. We just did it this morning. If I want to find the average of anything, I integrate whatever it is I'm averaging. The time period for the average is 0 to 4. So I must divide by the length of the time period. So I have to write that if I expect to get full credit. That's my y. That's the integral that's required. Questions? Cool. The how is just use my calculator. So here, fraction to start with. Make sure you use the fraction bar. The slash tends to cause mistakes, so I don't like you using the slash. That's the average velocity, 0.358. Probably get 2 points on the AP test for doing that right there. So. Questions? Oh, please, Amy.
Do you need units for that?
If the problem had units specified, the units would absolutely be essential. In this case, they didn't actually specify any units, so you don't have to. 2 points. Oh, go ahead.
How do you get fractional calculator?
No worries. So just hit the alpha key, and then the y equal. And then just enter. Does that make sense? Yeah. Good question. 2 points. Edward.
Going back to the units thing, is this just one of those situations where out of an abundance of caution you put units anyway and just...
I don't think they would dock you if you had units.
So it's not
As long as they
a-
made sense. Like if you put feet per second, miles per hour or something. You really don't have to if they don't specify them. But I don't think they would take points off. Is that what you meant?
Yeah.
2 points. Please.
On this one, does it matter if it has the approximate sign or the actual?
I like that question a lot. Technically, when I use my calculator, I'm approximating because the calculator can't do a perfect integral. However, on all of the documentation as to how the AP test is scored, they always use equal signs. So I just follow them. I don't think they're overly picky on that one. Good question, Logan. Anybody else? Okay, next thing. Extra example 3H, calculate the average speed of the object. We learned some time ago that speed is the absolute value of velocity. If I'm supposed to find average speed, I'm going to integrate whatever it is I am averaging. So I'm going to integrate the absolute value of the velocity. Question? Cool. Take out my calculator, type it in. Fraction. Dumb. Math 9. Now I need the absolute value bars. I have a hard time remembering where they are. There's lots of different ways to get to them. My favorite is I use the catalog. Catalog is a list of all calculator functions. Absolute value starts with A, B, so it's the first one on the list. So the catalog is down here on the 0 key. So I just go second function, 0, and the very first choice is absolute value, like that. Just wave, if you need me to show it again. So second and then 0. You see there's a little more catalog above the 0. And then the first one is absolute value. Just wave, can you need me to show it again? Now I want to take the absolute value of the velocity, so that's just alpha trace to dx. Press enter, collect my points. The average speed is 0.597.
Wait, why is it different than the other one? Because it's actually doing but it's something that's already started.
So in this problem, the velocity, let's look at a graph. So we have in our calculator the formula for velocity. If we hit a window of 0 to 4 and zoom fit, we'll see a plot of all the different velocity values for all those different times. And we'll see that the velocity is actually changing from having positive velocities to negative velocities. So when I average the velocity, I'm averaging all those positive and negative values together. And so they kind of counteract each other a little bit. For example, this right here would be a velocity of 1. So the average of all these different velocities, because these negative velocities get counted as negatives, that average turns out to be, what was that? 0.358. But the speed is all of the velocities, just the numbers, no negative. So a graph of speed would look like this. And so I'd only be averaging the positive values. That's why I get a higher average. that answer your question?
Yeah.
Point. Cool. Okay, the blue packet is what I will be asking if you've completed when I see you on Monday.
Extra examples?
Yeah.
We've done all the extra examples now. So there should be no longer any extra examples. Oh, yeah, but you know how to do that.